Chapter 4 is about reactor. The full title of Chapter 4 is Synthesis of Reactor Flow Sheet and Selection of Reactor Process Conditions. In this Chapter 4, you will learn about selection of reaction pathways, which is the review of Chapter 1, comprehensive material balance equations with chemical reactors, quantitative measures of reactor performances, the effect of chemical reaction equilibrium and chemical kinetics on reactor performances, and ways to design and operate reactors for optimal output. Okay, so here is the list of industrially important chemical reactions. There are several categories of chemical reactions. The first one is oxidation, hydrogenation and dehydrogenation, polymerization, hydrolysis and dehydrolysis, halogenation and other substitution reactions, isomerization, and ring opening and closing. Please read the chemical reactions for each categories like cooking, bleaching, and disinfecting is involved in oxidation and so on. Rules of thumb for initial selection of raw materials and reaction pathways. We have several points for considering to maximize our output and to save our cost. The first one is material economy, and also the other economy is related to energy economy. Of course, we should think about the safety, and we want to have no side reactions. And the characteristics of reactions should be simple and fast. Here is an example about the process analysis and to calculate a measure of whether the process is effective or not. The example 4.1 is about the improved synthesis of ibuprofen. As you know, ibuprofen is the painkiller. We have popularly used the ibuprofen for suppressing the pains. We have two processes. The first process involves 6 steps, and the other process have 3 steps. I'd like to compare between those two processes by using the generation consumption analysis with an atom economy as a measure of what kind of process is preferred. Can you remember how to use the generation consumption analysis? We should try to make a stoichiometry coefficient table for analyzing each process. For the first process having 6 different steps, I'd like to make the stoichiometry coefficient table. In the first column, list all of the chemicals involved in those 6 steps. So all of them here, and the second column have the stoichiometry coefficient for the first reaction, and then second reaction, third, fourth, fifth, and sixth 6 reactions. For example, C10H14 is involved in only the first reactions. So let me check the stoichiometric coefficient of this compound. 1 as the reactant. So I have written down -1 for the C10H14. Let me check the other compound. For example, C12H16 oxygen. So you can find this compound in the first chemical reaction equation and also second chemical reaction equations. This intermediate is generated in the first reaction, and also this intermediate is consumed again for the second reaction. So you should fill out the blank about the first chemical reaction like +1 because this is the product, and in the second chemical reaction equation you could find -1 as the stoichiometric coefficient of this compound. So maybe the net summation of this of the stoichiometric coefficient for this compound would be 0. After the column for each reaction, you could find the net summation of the stoichiometric coefficient for this column. Sometimes you could find minus sign, sometimes plus, and blank um, indicates the net summation is 0. So it means C12H16O is the intermediate, and it cannot be found in the final product. The other column is about the information of molecular weight because atom economy or AE is based on the mass of product and also mass of the reactant. Let me calculate the atom economy. Atom economy is defined as the product per reactant in terms of the mass. So in the numerator you can find 206 because this one, this is the ibuprofen is the desired product, so 206 on the numerator. In the denominator, I'd like to sum all of the reactants. In the net summation column, you can find several minus signs. It means they are the reactants. So 134 for the first compound, for the second compound 102, and then 133.5 and 108, 122.5, 68, 36.5, 33. The summation of all reactants is located in the denominator. So the atom economy is calculated at 28% or 0.28, which means 28% of reactant is converted to the product. So the atom economy of the first process is 28%. Let's go to the second process. This second process have 3 steps. And then, of course, we should make the stoichiometric coefficient table, and then let me try to calculate the atom economy for the second process. Product mass and reactant mass. The result is 77%, which indicates 77% of reactant is converted to the product. Therefore, we have the higher values of atom economy for the second process. You would prefer the second process in terms of atom economy. We did the generation consumption analysis, and we have used the atom economy as a measure to estimate which process is preferable or not. Let me think about what are the reactor design variables. Temperature and pressure, volume, residence time, reactant composition, and catalyst. Temperature and pressure is controlled to maximize the conversion of raw material to desired product, while reducing or eliminating undesired reactions. The second one is volume, and the reactor volume is chosen on the basis of the volume of material and the time required for the desired reactions. I'd like to define the residence time or tau. The residence time tau is the time that the material stays in reactor. Here is some examples. You have a 1-liter reactor and the reactants and products are flowing in and out of the reactor at 1 liter per hour. In this case, the retention time of reactants and products is 1 hour, which is obtained by dividing the volume by the flow rate. 1 liter per 1 liter per hour. Then we could obtain 1 hour as the retention time. Let me increase the volume from 1 liter to 2 liter at the same flow rate. Then the residence time increases from 1 hour to 2 hours because we have larger volume. Or let me increase the flow rate from 1 liter per hour to 2 liter per hour with 1 liter reactor. In that case, the residence time of reactants and products are reduced into 0.5 hour because we have used faster flow rate to and out of the reactor. Reactant composition. Sometimes we could use the stoichiometric feed ratio. Sometimes we could use non-stoichiometric feed ratios. The non-stoichiometric feed ratios might be chosen to minimize unwanted byproducts or to ensure complete conversion of the most expensive reactants. We have the chemical reaction equation here, A plus B as reactant, which is going to P as product. Your first choice would be the stoichiometric feed ratio. So in this case, A to B is equal to 1 to 1 as the feed ratio. Then, if we could obtain 100% conversion at this stoichiometric feed ratio, then this feed ratio would be accepted. However, sometimes this stoichiometric feed ratio is going to very low conversion. Then you should think about the second choice, which is the non-stoichiometric feed ratios to the reactor. Here is two situations. You have used 1-to-1 for the A to B, then you have obtained the 60% conversion. In the second situation, you have used a non-stoichiometric feed ratio, like 1 to 2. In this case, of course, you could easily expect that some portion of B cannot be reacted with A because we have more amount of B from this stoichiometric ratio between A and B. However, in this feed ratio, I have obtained 90% very high conversion. So, which situation is better for you? In my case, I'd like to choose the stoichiometric flow rate for obtaining the higher conversion. The last reactor design variables in this slide is catalyst. Catalyst is used to speed up reactions, to reduce the size of reactors and save money. Catalysts are used sometimes to proceed reactions at low temperatures or ambient pressures, thus increasing the safety of a process. Catalysts could be sometimes oxygen bases, sometimes solid metal catalysts like platinum catalysts, or sometimes enzymes in food and pharmaceuticals. We are still on reactor design variables, and operational mode could be the reactor design variables, which is sometimes batch, sometimes continuous flow, sometimes semi-batch mode. Batch mode is characterized by time variant concentration. We have some concentration profiles. X-axis is the time, Y-axis is the concentration of reactants and product. In the batch mode, the concentration of the reactants like A and B would decrease a long time, and at the same time, the concentration of the product C is going up and increases a long time. Let's go to the second operation mode, which is the continuous flow mode. That is characterized by time invariant concentration. In the continuous flow mode, usually we have assumed the steady state. So, the concentration of A and B, also C as a product, is not changing during reaction time. That is the continuous flow mode is working on steady state. Semi-batch mode is the in-between mode between batch and continuous flow. The semi-batch mode is popularly used for polymer synthesis or fermentation reactions. The other reactor design variables could be mixing patterns. Two types of concentration distributions are popularly assumed. The first one is stirring mixing pattern, results in homogeneous distribution of reactants, products, and intermediates. You can find this stirring mode is in batch reactor, sometimes continuous stirred tank reactor, CSTR. In this case, concentration is the same at every location inside the reactor. Even if concentration inside the reactor may change with time. I mean, at a specific time, you could find the same concentration at every location inside the reactor, such as batch and sometimes continuous flow reactor. The other thing is plug flow reactor, and plug flow, something like that, is assumed when a flow is introduced into a pipe type reactor. This reactor is a kind of pipe, and from the top some reactant is introduced into the reactor, and then this media is flowing along the z-axis and finally going out of the outlet of the pipe type reactor. Inside of reactor, usually we have assumed this kind of plug flow. Even if the real situation we would meet the parabolic flow profiles. For simplicity, we are assuming the plug flow profiles inside of plug flow reactor. Concentrations change along z-axis. So at the inlet, the concentration of the reactant is maximized and the concentration of product is minimized. However, along z-axis or along the distance from the pipe inlet to outlet, then the concentration of the product would increase continuously as the reaction proceeds. However, no radial distribution of concentration at a fixed G location is allowed. So let me take a point along on the g-axis, like let me say this point, and at this point, at any location along the radial direction, we have the same concentration for reactant and product. However, again, the concentration change along g-axis. That is the mixing patterns. We have two mixing patterns introduced. The first one is complete stirring. The other thing is plug flow. Here is the subchapter 2A about the reactor material balance equations with known stoichiometry cases. As you know, we should think about the use of extent of reaction, Xi. The extent of reaction Xi is defined for a single chemical reaction equations. I mean, for each chemical reaction equations, you could define a single extent of reaction Xi. The definition of the extent of reaction is equal to the reaction rate of species I, which is normalized by the corresponding stoichiometry coefficient. Therefore, the reaction rate can be described by the extent of reaction with the stoichiometry coefficient. I is index for the compound involved in the chemical reaction equation, and K is the index for the chemical reactions. The choice for the material balance equation depends on the operational mode of reactors. Anyway, if you have balanced chemical reaction equations, it would be better to use the mole balance equation instead of mass balance equation. And in a continuous flow mode, you don't have any accumulation, and in minus out plus generation term is equal to 0. Therefore, out is equal to in plus generation term. The generation term is calculated by using the extent of reactions. Let's go to the other extreme, which is the batch mode. And for the batch mode, usually we could use the integral form of mole balance equations, or sometimes differential form of mole balance equations. In the batch mode, accumulation is there, so this accumulation can be described by final minus initial is equal to no input minus no output plus generation term. Or in the differential form of mole balance equations, the accumulation is here, dn dt for the system is equal to no input minus no output plus generation term. The semi-batch mode is going to the most complicated mole balance equations. Here is the integral form of the mole balance equation. Accumulation, which is the final minus initial, is equal to input minus output plus generation term. For each term, you should use the integration. Here is the example 4.2 that is about natural gas combustion. In this case, we have known that the balanced chemical reaction equations. Let me read the problems or examples. Natural gas produced over eons by decade of ancient plants is recovered from wells and used widely as a source of heat and energy. The composition of natural gas varies from well to well. Here are analyses of natural gas from three different sources. The first one is coming from the New Mexico, Rio Arriba, and the other thing is San Juan from New Mexico, and the other thing is Cliffside from Texas. Natural gas have methane, ethane, propane, butane, pentane. Those five compounds are alkanes, plus some carbon dioxide and nitrogen. We know the compositions of each natural gas for three different sources. In this example, we'd like to use the first source, natural gas. A furnace operating at steady state, I have said steady state, it means we have no accumulation, burns 1.00 mmSCFD. mmSCFD stands for million standard cubic feet per day of natural gas from Rio Arriba, with 23.0 mmSCFD air, assumed to be 79 mole percent nitrogen, 21 mole percent of oxygen. It means here is the furnace and we have two input streams. The first stream has natural gas, and in the natural gas we have 1, 2, 3, 4, 5, 6, 7 compounds there. And the other thing is air. And in the stream 2 we have 2 compounds in air. The only detectable compounds in the flue gas are CO2, H2O, oxygen, and nitrogen. It means we have done the complete conversion inside of the furnace. Complete combustion of hydrocarbons, including methane, ethane, propane, butane, pentane, is described by the general chemical equations like CXHY standing for the alkane plus oxygen is going to CO2 and water. There's some unknowns including X and Y, which depends on the chemical formula for each alkanes. It means we have 5 different balanced chemical reaction equations because we have 5 alkanes in the natural gas. The question is that what is the flow rate in kilogram mole per hour and composition mole percent of the flue gas? Here is the diagram for describing these problems, and let me check the degree of freedom. The first one is freedom or unknown or variables. I'd like to take the compounds as the components for the mole balance equations. So we have 1, 2, 3, 4, 5, 6, 3, 5, 6, 7. 7 input variables for the stream 1 and 2 input variables for stream 2 and 4 output variables. Plus, we have 5 alkanes. It means we have 5 balanced chemical reaction equations. It means we have 5 extent of reactions for the unknowns. So plus 5 xi. Then it is going to 18 unknowns there. And then let me count the number of restricts or equations. For the input composition, we have 6 input for the stream 1 and 1 input for the stream 2. Actually, in terms of the composition, we have 1, 2, 3, 4, 5, 6, 7. 7 values about the composition. But I have said 6 inputs because the total summation of this composition is going to 100%. So only 6 compositions are independent to each other. So 6 input. And the same thing for the stream 2. We have 2 composition values like 79 mole percent nitrogen and 21 mole percent oxygen. However, only 1 values are independent. So 1 input. Plus, we have 2 flow rates for stream 1 and stream 2 respectively, like 1 mm SCFD for stream 1 and 23 mm SCFD for the stream 2. So 2 flow informations. Plus, we have 9 mole balance equations because the 9 compounds are available in these systems. Let me count the variables. 1, 2, 3, 4, 5, 6, 7, and the same, and 8 oxygen, and O2 N2 is involved in this 8, and plus H2O and CO2, but CO2 is overlapped with here. So totally 9 compounds are involved in this process. So 9 material balance equations. Then 18 restrict. So degree of freedom is going to 0. It means we could solve these problems. And then let me try to calculate some flow rate and composition. We have some bases here, 1 mm SCFD and 23 mm SCFD air. The first one is for the natural gas flow rate. mm SCFD is the volumetric flow rate, but it would be better to convert the volumetric thing into molar thing as the flow rate, because we know the value the values of the stoichiometric coefficients for the balanced chemical reaction equations. In that case, mole is the best as the unit for the flow rate or some quantities inside of the systems. So, for example, for the natural gas, we have 10 to the 6 cubic feet per day because SCFD is the million standard cubic feet per day. So I'd like to change this volumetric flow rate into the molar flow rate in kilogram mole per hour. So how can we convert the volume of gas into moles? We could use the ideal gas law. The molar flow rate is equal to PV. Actually, V stands for the volumetric flow rate per RT. And V dot is going to here for the natural gas. And pressure, this volumetric flow rate was obtained at the standard state. The standard state, I mean, not standard state. This standard indicates standard temperature and pressure. So sometimes shortly STP. The STP, or standard temperature and pressure, indicates 1 atmospheric pressure, or 1 atm, and 0 Celsius degree. So as the pressure value, I could use the 1 atm. And then I'd like to change the day to hour. So this is the conversion factor. And here's the PV in the numerator. And let's go to the denominators. Temperature 0 Celsius degree, which is going to the 273.15 Kelvin. The other thing is the ideal gas constant, and in this case I have chosen the 0.082 liter per atm, liter by atm per gram mole K. So atm here and then Kelvin here. However, we are still using the cubic feet. So I'd like to change the cubic feet to liter. So here is the conversion factor between cubic feet with liter. And also, I'd like to convert the gram mole to kilogram mole here as the conversion the factor. Then we could obtain 52.6 kilogram mole per hour for the 10 to the 6 cubic feet per day. So this value is about the natural gas. The other thing is air. We have used the 23 mmSCF, the air. So 23 by 52.6 is going to 1210 kilogram mole per hour. So right now we have changed the volumetric flow rate into molar flow rate. Then right now in the natural gas we have 5 different alkane compounds. It means we have 5 different chemical reaction equations which are well balanced. Also, this furnace is operated on the continuous flow mode, then you don't need to think about the accumulation term. So knowing accumulation is equal to in minus out plus generation term. Then let me set up the mole balance equations. Again, we'll use this equation. Out is equal to in plus generation term. We have several compounds. Actually, we have 9 compounds are there, and 5 among them is related to alkane compounds. So let me set up the mole balance equation for each compound. For the methane, the initial input value of the methane is found in natural gas, which is the 50.98 kilogram mole per hour. And then let me think about the generation term. The methane is found only in the chemical reaction equation number 1. X equal in that equation, x equal to 1 and y equal to 4. So the generation term is the product of xi1 for the chemical reaction equation 1 with minus 1 as the stoichiometry coefficient. So this value plus this value is going to 0 because there are no alkanes found in the output stream from the furnace. This is the first equation for the molar balance equation. For the ethane, in the same way, we have made the mole balance equation. Methane, ethane, propane, butane, pentane. Then we have 5 equations. And how about the CO2? In the natural gas, we have a CO2. this is the amount of CO2 in the natural gas, and nothing in the other stream for the input. And let's go to the generation term. For every alkane combustion, the carbon dioxide is produced. Xy1 for the methane combustion, Xy2 for the ethane combustion, propane combustion, butane combustion, and pentane combustion. Also, the stoichiometry coefficient of CO2 is X in the alkane. I mean, X is the number of carbon. So, plus 2, plus 3, plus 4, plus 5, and plus 1 for the first chemical reaction equation. Then is equal to the number of CO2 in output. Let's go to the nitrogen. Nitrogen is found in the natural gas, also air. So the summation of those two resources about the nitrogen is going to the input amount of nitrogen. And nitrogen are not involved in any chemical reactions. It means this value is just going out of the furnace. Let me think about the oxygen. Oxygen is always consumed for every alkane combustion. So in the input, oxygen is found in the stream 2, and as the generation term, the oxygen is consumed for Xy1, Xy2, Xy3, Xy4, Xy5. Also, the stoichiometric coefficient of the oxygen combustion or oxygen consumption is x plus y over 4. Then these 2, 3.5, 5, 6.5, 8 values are coming from the stoichiometric coefficient of x plus y over 4. Then you could find some oxygen in the upstream. How about water? Nothing in input. However, water is generated for all of the 5 combustion reaction equations. And then you could find the H2O in the upstream. So right now we have 9 mole balance equations. And from the first 5 equations, you could calculate the extent of reaction Xi for chemical reaction equation number 1, 2, 3, 4, 5. And then by using the value, then you could calculate the output variables for CO2, N2, O2, and water. That's it. Another example with the balanced chemical reaction equations. Example 4.3 about ibuprofen synthesis. Ibuprofen, the painkiller, is synthesized from C10H14 and acetic anhydride, H2, and carbon monoxide in a 3-step reaction scheme like that. This reaction is carried out in a batch reactor. And initially the reactor is charged with 1.4 gram more C10H14. The other thing is 1.4 gram more H2, 3 gram more, and 2 gram more carbon monoxide. The reactor is brought to reaction temperature and held there for 2.3 hours. So we are using a batch reactor and the reaction time is 2.3 hour. So it would be better to use the integral form of mole balance equations. Let me check the mole balance equation. Final minus initial, that is about the accumulation, is equal to no input, no output plus generation term. So in this table, you can find the compound involved in those 3 reaction steps. And then the initial amount in the second column, 1.4 for the C10H14, the other 1.4 for the second chemicals and 3 more for H2 and 2 um, gram more for carbon monoxide. For the other chemicals, we didn't introduce them. Then that is the initial amount plus generation term. Here, the extent of reactions were given to you for each reaction. Reaction 1, 0.39 gram mole per hour. About reaction 2, 0.35 and 0.30 gram mole per hour for the third reaction. So we could use the xi values. So let me check about C10H14. C10H14 is the reactant in the first reaction. So minus sign with the extent of reaction and during 2.3 hour. That is the amount of the C10H14 generation time. So actually it is consumed because we can't find the minus sign for the value. So the summation of those two terms is going to the final content of this C10H14. How about the second reactant? The same thing. And the third one, C12H16 oxygen. This is a kind of the intermediate. This intermediate is generated from the reaction 1 and at least some portion of this intermediate is consumed in the presence of hydrogen. So the net generation term is that the plus 1 from the stoichiometry coefficient of this compound in reaction 1 by 0.39, that is the xi1 with 2.3 hour. And then let's go to the second reaction. The minus 1 is the stoichiometry coefficient for this compound here with 0.35 is the xi2 for the reaction 2 and 2.3 hour. So the resultant value coming from those calculation is about 0.09 moles for the final amount existing inside of the reactor. So in this way we could calculate the values of each compound in the reactors after 2.3 hour. That is the ibuprofen synthesis inside of the reactor for the batch mode for 2.3 hour. The other example. The last reaction in the three-step ibuprofen synthesis in the previous slide is this one. And then here carbon monoxide is involved for making the ibuprofen. Because carbon monoxide is a highly toxic gas, the reactor is designed to be operated in semi-batch mode. The most complicated version of the mole balance equations should be used. Initially, 1.5 gram more the first reactant is charged to the reactor. Carbon monoxide added at a rate of 0.3 gram mole per hour during the reaction. So it's the reason why we call this situation as the semi-batch, because carbon monoxide is continuously added to the reactor during the reaction time. To keep the concentration of carbon monoxide inside of the reactor low. If the reaction rate under these conditions is 0.27 gram mole per hour, so this is the value of the extent of reaction for this reaction. How long should the reactor be operated to produce 1.2 gram more ibuprofen? This is the target amount of ibuprofen production. What is in the reactor at the end of the operation? It means we should calculate the concentration of this one, and this one. So right now we have 3 compounds for these problems, and then it means we could make the three different mole balance equations. So I'd like to use the integral form of mole balance equations. So the first one is for ibuprofen, the second one is the first chemical, and the third one is carbon monoxide. Um, Final minus initial is about the accumulation term is equal to input minus output plus generation term. So final term for the ibuprofen is 1.2 gram more at the end of the reaction. So that is our target. And at the very first time, we don't have any ibuprofen in the reactor. No input, no output, and the last term is related to the generation term. So um, the product of the stoichiometry coefficient of ibuprofen with the extent of reaction, then you should multiply the time. So what is the stoichiometry coefficient of ibuprofen in these chemical reaction equations? Of course, plus 1 with xi. Xi is the 0.27 gram mole per hour. And then some time. So inside of the integral operation, we have 0.27 gram mole per hour. Then 1.2 from here is equal to the integral of 0.27 dt over 0 to some t hour. Then 1.2 is equal to 0.270. Then we could expect the value of the reaction time to obtain the 1.2 gram more at the end of the reaction. So the answer is reaction time is equal to 4.44 hour. Let's go to the second more balanced equations about the first chemicals C12H18 oxygen. Final minus initial, that is the 1.5, plus no input and no output plus generation term for 4.44 hour. This value comes from the first mole balance equations. And then we could calculate the final concentration of the first chemical. How about carbon monoxide? The same. Uh, the final amount of carbon monoxide is equal to the input. Yes, we have. And minus output, nothing there, plus generation. So this is going to there, and we have introduced about 0.3 gram mole per hour of CO2 into the reactor. So 0.30 with some integration for 4.44 hour, and also carbon monoxide is consumed, which is expected from the the balanced chemical reaction equation here, and then minus 0.27 dt. So finally, we would have the 0.13 gram more of carbon monoxide inside of reactor after the 4.44 hour reaction in the semi-batch reactor. Until now, we have solved the problems having some non-stoichiometric coefficients in the balanced chemical reaction equation. From this slide, I'd like to say about the examples having no stoichiometric coefficients without the balanced chemical reaction equations. Situations for unknown stoichiometry. The raw material is highly complex, and the molecular formulas are unknown or uncertain, like natural materials containing wood or coal. The second situation is that the reaction network is highly complex and the reaction products are unknown or uncertain, like combustion and degradation reactions. If the elemental composition of the raw material and/or reaction product is known, then use elements as components. So I'd like to emphasize this final sentence. In the case of unknown stoichiometry, simply use elements. And one more thing, elements do not undergo chemical reactions. You cannot make, for example, nitrogen. You cannot consume the carbon as atoms. It is not the compounds, it is elements. Here is the example about the unknown stoichiometric coefficients problem. Example 4.5, natural gas combustion. So we went back to the furnace, and natural gas are introduced into the furnace in the stream 1, input stream number 1, and in the input stream number 2 we have two compounds, air, nitrogen and oxygen. And then in the output stream we have carbon dioxide, water, oxygen, nitrogen. Uh, we have as flue gas to atmosphere. The natural gas have five alkanes like methane, ethane, propane, butane, pentane, plus CO2 and nitrogen. Of course, we have know the amount of each alkanes and carbon dioxide and nitrogen. Also in the stream 2, we know the amount of nitrogen flow rate and oxygen flow rate. So let me use the elements as the components for the material balance equations, because in this example or problem statement we don't have any information about the chemical reaction equations. So let me change the values about the molecules to the values of atoms. For the natural gas stream, we have 5 alkanes plus 2 more compounds, CO2, nitrogen. And what we know is the flow rate in input streams. We could easily convert the flow rate for each compounds into the flow rate for each element like carbon, hydrogen, oxygen, and nitrogen. So for the carbon, you could calculate um, the amount. There are several carbon sources like 5 alkanes plus CO2. And in CH4 we have just one carbon, so the amount of the carbon flow rate in methane is 1 by the input flow rate for methane. How about the ethane? Ethane has 2 carbons, so 2 by 0.70. That is the input flow rate. Then it is going to 1.4, something like that. And summation of all flow rates about the carbon atom from the carbon resources, then we could obtain the value about the carbon molar flow rate. In this case, 53.28 moles per hour or something. Okay, moles per hour, right? How about hydrogen? In the same way, you could calculate it. We have 5 hydrogen sources. The summation of those 5 hydrogen sources by considering the number of hydrogen in those molecules, then you could obtain the total values of hydrogen flow rate, hydrogen atom flow rate. How about oxygen? Oxygen is found in only CO2. So we have 2 O atom, oxygen atom in CO2, then 2 by 2 by 0.43 is going to 0.86 mole per hour. How about nitrogen? Only one source here, N2, and then 2 times of 0.36 is going to 0.72. Then right now we have the flow rate in input stream for each atoms. Also, for the airstream, we could easily calculate the nitrogen and oxygen atom flow rates here. Then let's go to the mole balance equation for element. There are no accumulation for this steady state operation for the continuous flow mode, and then it's equal to in minus out plus no generation, no consumption. That is to say, for each element, in is equal to out. It's very simple. That's it. Then let me start with nitrogen atom, then hydrogen, then carbon and oxygen. Uh, Nitrogen input is equal to the value from the natural gas stream, like 0.72 for nitrogen here, and then 1912 kilogram mole per hour from the stream 2 of the air. Then summation of those two, nitrogen flow rate is going to the upstream of nitrogen element. So this value, and nitrogen atom leaves as the nitrogen molecules having two nitrogen atom. So this value is divided by 2 is going to the molar flow rate for nitrogen molecules in the upstream. And then let's go to the hydrogen. Hydrogen input is equal to output, and hydrogen input is this value, which comes from here. And then H leaves as water, and water have two hydrogen atom, so this value is divided by 2 is going to the value about the water flow rate in the upstream. Let's go to carbon, and here is the carbon flow rate, which can be considered as the upstream. Then carbon leaves as CO2, so CO2 has just only single carbon. Then this value 53.28 is the value of the carbon dioxide flue gas in upstream. Let's go to the oxygen. Let me sum the amount of oxygen atom from the air, like 508, and then in the natural gas stream, which is the 0.86. It's totally this value for the upstream for the oxygen atom flow rate. Then let me calculate the amount of the water, carbon dioxide, and oxygen, actually oxygen molecules in the upstream. So this value, I mean the output flow rate of oxygen atom is equal to the flow rate of water, and the flow rate of carbon dioxide, and the flow rate of oxygen. The summation of those three sources is equal to the total amount of the oxygen atom in the upstream. So we know this value. And how about the water stream in the output? It comes from here, 104.67, and H2O has just only one atom of oxygen. Plus, how about CO2? CO2 value comes from here, 53.28, and carbon dioxide has two oxygens. So here's the 2. Plus, how about oxygen? We don't have any value about this information. Then oxygen molecules has two oxygen atom is equal to this one. So this is the unknown. I mean the unknown is the oxygen molecule flow rate in the upstream. So finally we could obtain that value. So right now we have the compositions in flue gas, like oxygen, carbon dioxide, water, and nitrogen. So let me remind you that this example is about the unknown stoichiometry coefficient problem.